Hey class, good morning. So again, this is fundamentals of machine design. Okay, so this is another topic. So this is the first topic we are going to introduce here is the flexural stress. Okay, so what is a flexural stress? Flexural stress, this is the maximum bending stress that can be applied to that material before it yields. Or flexural strength is also known as the bending strength. So modulus of rupture or transverse rupture strength. Okay, so if we look at the diagram, so on slide, so the beam is under simply supported, of course. Okay, so and the load P, of course, is applied at the midspan of the beam. But so actually, the support is fixed, or one end is fixed and another is a roller. Okay, so if we look at the stress that is applied, of course, at the upper portion of the beam, the stress is compression, and of course, at the bottom, from the midsection, of course, to the outermost fiber at the bottom is under tension. Okay, so actually, the basic equation for the flexural stress is sigma, of course, equals to mc over I. So if you remember your strength of materials, so this is the one that is also introduced in your subject. Okay, so where m now is the maximum moment, c is of course the distance from the neutral axis, of course the center of the beam to the outermost fiber or the extreme fiber. Okay, where I is the moment of inertia. Okay, so also, so moment of inertia can also be computed. Okay, so let us now consider an example here. Okay, so for flexural stress, determine the maximum bending moment of the beam loaded as shown. Okay, so we have a load, of course, at 4 meters from the support of 20 kilonewton, and at 8 meters we have 30, and of course at the other end is 10 kilonewtons. Okay, so first, taking summation of moment about A is equals to 0. Okay, so that is 20 multiplied by 4. Of course, the assumed A, of course, is the support at the left portion. Okay, plus 30 multiplied by 8 plus 10 multiplied by 4 is equals to 12 RB. Okay, of course, the support at B. Okay, so the reaction now at B is equals to 38.33 kilonewton. Okay, so taking summation of forces vertical and then getting the reaction at A. So the reaction at A is 21.67 kilonewton. Okay, so again, taking summation of moment, so that is summation of moment about A is equals to 0, or MB is equals to 21, multiplied by 4, that is 26 or 86.68 kilonewton meter. So the moment at C is equals to 86.68 plus 1.67 times 4 equals 93.36 kilonewton meter. So the maximum bending moment now is 93.6 kilonewton. So the moment at D is of course negative 20, and of course at E is equals to 0. Okay? So for variable stress refers to the application of different loadings such as fatigue, reverse, repeated, impact, or shock loadings. Okay, so if we look at the diagram here, so we have here the main stress and then the vertical or the stress, of course, amplitude. Okay, so we have here the Gerber's line, and then we have the Goodman line, and then we have here at the bottom we have the so-called the Safe Soderberg line. Okay, so and then we have here at the right portion of the slides we have the stress and time. So we have the maximum. You will identify the maximum stress and then the minimum stress, of course. Okay. So for variable stress, we are going to determine, of course, the average stress or the mean stress. Okay. So average, of course, is the summation, of course, divided by the number. Okay. Let us consider this. Okay, so the mean stress equals to the maximum stress plus the minimum stress over 2. Okay? For alternating, just subtract the maximum and the minimum and then divide it by 2. Okay? So you can easily determine the alternating stress of applied, okay, to the materials. So we have here the variable stress. Okay, Soderberg equation for ductile material. Actually, the derivation of this is very easy. So by similar triangle only considering the shape Soderberg line. Okay? So where the obtained or the derived equation now is 1 over n, or n represent the factor of safety, the main stress, and then the yield stress plus the factor, okay, the fatigue factor maybe. So multiplied by the alternating stress divided by the endurance stress. Okay, so for Goodman equation for brittle materials, so take note class for Soderberg uh, equation is only applicable to ductile materials, and the Goodman equation is applicable to brittle material. So for Goodman equation, that is 1 over n is equals to the main stress divided by the ultimate stress plus the fatigue factor plus or multiplied by the alternating over the endurance strength. So instead of using the yield strength for ductile, we always use the ultimate strength for a brittle material. Okay? So again, the nomenclatures of the equation we have here in, of course, the factor of safety. S max, the maximum induced stress. S min is the minimum induced stress. Mean or average stress, alternating stress, yield stress, ultimate strength, endurance strength, fatigue strength, or reduction factor. Okay, so in determining Kf, that is equals to 1 plus Q multiplied by Kt minus 1. Okay? Or Q is equals to 1 over 1 plus A over R. So what is Kt? So that is the stress concentration factor. Okay? And then Q is the knot sensitivity factor. And A is the factor dependent upon materials, ultimate strength, and R is the radius of stress razor. Okay? So we have here an example for variable stress. Okay, so example 1. The shaft whose torque varies from 200 Nm-pound to 2,000 rather, to 6,000 Nm-pound has a 1.5 inches diameter and a yield strength value in shear of 60,000 psi. Compute the shaft mean stress, okay? So the torque minimum, of course, is 2,000 and the torque maximum is 6,000. Diameter is 1.5, okay? So knowing that the stress is equals to 16T over pi d cube. Okay, so getting now the value of the stress. So that is, the minimum is 3,018.05 psi. And getting the maximum stress, the computed value is now 9,054.15 psi. And getting the alternating strength, or SA rather, so that is 9,054 over the mean stress rather, okay? So that is 6,036 psi, okay? So that is not the alternating stress, but that is mean stress. For alternating stress, you just subtract here. So this is typographical error class, okay? So, and then the variable stress, okay? So we have here example number 2. So calculate the factor of safety resulting from the following stress values. Yield strength equals to 60 psi, endurance 20, average stress SM 15 psi, and alternating stress of 10 psi. Okay, so given, and then solution from the Soderberg equation. So the factor of safety now computed is 1.33. Okay, so Thank you very much, class.